Hey everyone, I'm Ganesh Devarajan. I work for Tipping Point, part of the DV Labs, and I'm currently researching into SCADA. So, yeah. So, firstly, welcome all. And if there's still anybody here for Dan Kaminsky's speech, I think it's in track 3. So, go there. All right. Here's the agenda for today's talk. I'll be talking about general overview of SCADA first, and then give you about some ideas about the protocols and why do we need security in SCADA protocols and how we can secure them a little bit, and about the fuzzer, which is not being released. Sorry, the fuzzer framework has been released, but the SCADA part is not being released due to some people who were pretty upset about me releasing it. So I'm holding it back to it. I don't know. There are lots of talks. And about the basic future work and everything. Firstly, I don't know if everybody over here knows what SCADA. Everybody's got an idea about SCADA. If not, here's the definition. And I'm just going to read it out for you guys. SCADA is supervisory control and data acquisition. It's defined as the common process control application that collects data from sensors and on the shop floors or in the remote locations and sends them to the central computing for management and control. And SCADA's got different definitions both in the United States, in the Northern America, and outside the world. And as you can see, those are two things. All right. Where is SCADA mainly used? It's used in all the critical infrastructures and all the utility companies. And these are all the places where you can find SCADA more regularly. And some of them are really not secure. And you will see why. And what is the basic infrastructure of SCADA network? We started with I'm just going to come up from top to down, where the operator, the human, who looks into all the fancy GUI provided by the different vendors, and then looks into it and makes the decision. And he gets to make the decision only when there are some kind of cases where there have been flags raised by the RTUs or the MTUs. And the human machine interface, which is all the fancy GUIs provided by the vendors. And this one interacts with the MTUs, which are the master terminal units, which are one step above, and they collect information from all the other remote terminal units, and then see what they process the information, and then raise a flag if it needs to be, that kind of thing. Then the communication channel. Right now, supposing you have a SCADA network which is has got 2 plants, one probably in the East Coast and one in the West Coast. So it does go through the internet, and some of them are open channel, clear text kind of a thing. So good luck with that too. So, and there are other SCADA networks too, where it's in a smaller network, manufacturing units or those kind of things, where it's all local, and you have wireless and those kind of things used there too. And the remote terminal units, these are the units which basically sends out instructions to all the end nodes and gets out the sensors. They send out queries to them asking what's the temperature that you're reading, or what is the number of units that you still have, those kind of things. And these data are sent to the MTUs, and then the MTUs are sending it to the HMI, and the HMI processes them and then puts it out to the human operator. This is how the traditional SCADA network used to be, where the blue line on the top that you see is where the internet is being used, Ethernet is being used, and the rest all are the device level network and proprietary kind of network, those kind of things. And initially they all used to be RS-232 and those kind of networks. And somebody's coming. And later on, now it's a little bit more internet, you see more blue lines all over the place. And there are still plans which are following this kind of a network, where they have still device level networks still going on in most of the places, and internet on the upper level, those kind of things. And this is how some of our current, I think it's the gas industries, which is most of the gas industries have already taken up Ethernet, even for the RTUs and those kind of places. And in the future, you will find all of them, almost every single SCADA network being this way, with internet all over the places. So you can communicate to every single node and request information what's the temperature, or what is your current readings, and just shut down and just listen to whatever the server has to say, that kind of thing. You can send in all sorts of details to them. Why do we need security in SCADA? And like initially, like Modbus was like created in like 1970s, and it's still being used widely. And like the vendors, they're still coming out with like new Modbus softwares and like releasing it out, like those kind of things. And late 1970s, you can imagine how it was there and like now. And there isn't much improvement done there. Like they used to have initially like Modbus RTU, then Modbus ASCII, which I'll be like discussing more in detail like in the future slides. And they just decided, okay, let's put it on TCP/IP and let's communicate through the internet. And they just put it up, and without even giving a damn about security and those kind of things. And like, and they all go in clear text, and like you just can communicate to any single node over there, which is like exposed to the internet. Then, okay, so the whole problem about having SCADA network over the internet is like it's kind of easily exposed, and like, I mean, if you don't have proper defense, I'm sure like there are many people like, if it's like really important infrastructure, they have all sorts of defense mechanisms around it, so that like hackers don't get into it and like do anything to it. But what about like the cases like where like you have like small manufacturing units, small companies? They can spend tons of money on like security and like putting in all those kind of like defense mechanisms over there. So they are much more vulnerable to this. And like there are cases where like you have like nodes which are like, even though they have all the defense parameters and everything set up, one or two nodes just happen to be like dangling out, because like this is like such a widespread network. They're like dangling out, or like somebody from inside the network could as well take control of these nodes and then use them to attack the servers too. So, and the funny thing about SCADA networks is like the protocols like Modbus and all, like you just send an instruction to it, it's going to like send back a response to. I mean, like it doesn't matter, like it's not going to verify like if you're like the legitimate server who's sending it out, or like are you a legitimate client who's sending out this instruction. So you just send a reboot command to like the server just goes blindly reboots. You don't have to authenticate or do anything of that sort. And yeah, suppose there's this one example that I like to give, which is like you have like company A and company B who are like doing the same thing, say Dell and HP. And HP wants to take over Dell, and one easy way to do is like take control of the SCADA system, burn down all their servers, saying like, the temperature reading is say like at 68 for the server rooms, just provide false data over there saying it's 68 while all the servers are burning down over there. And by that, like the entire infrastructure of the company is gone, like all the data is lost, but without even having to like hack into like every single computer and like taking it down, that kind of thing. So it's much more simpler to hack it down if there isn't proper defense mechanism around it. Yeah, current security scenarios are like poor authentication and verification of the client nodes. Like I told you before, like you can send out instructions to the server, or like the servers, you can pretend to be the server and send out instructions to the client and say like do this, and like, it's just blindly going to do it. Like protocols like Modbus and DNP3. Whereas like in ICCP, we have to do a little bit more jazz of like doing like the entire authentication portion, and then like doing like the connection, like the three-way connection, and then like going about doing the hacking over there. So I will explain those two, I mean all the three of them, where like how those connections and everything works, and like you can see those things too. And like most of them are like running on like really old Windows platform or like Linux platform, and there are like so many platform-based vulnerabilities which still can be exploited too. There are like cases where like you go about, what do you call, like exploit like some known vulnerabilities, some 0 days, or like even like some old ones, because half the systems are not being able to like, what do you call, they are not able to patch them up because of they need to have like maximum uptime, because the moment the server goes down, they have to like do all sorts of maintenance things and everything, which takes a lot of time, and like, they are kind of like a little bit hesitant about it. So, and most of them have the belief that like, oh, nobody's going to hack into these kind of small manufacturing things. And it depends, like, if you're really small, nobody even gives a damn about it. And like, if you, as you grow up, that's when people start caring. I mean, like, if you're in a manufacturing plant or something like between two companies, I mean, like, if companies like Dell and HP, for example, I'm not marketing for anybody, by the way. So, yeah. And if you really want to like take over one company instead of the other one, like they themselves could do such kind of an activity to like take down the other one. Then, yeah, like you see, like the vendors believe, they think nobody's going to hack into my network, and my network is the securest one of all, the kind of thing. I guess so. and the attack scenarios. So one of them will be like providing false status. So supposing you in a water plant, you have water sensors, which basically looks for like if there's any pollutants being added into the water, and if you can fudge that data, which is going back to the servers saying like, no, there's no pollutants over there, and like you put in like some kind of pollutants into the water, and like that entire thing gets distributed to everybody's house, and like you drink, you fall sick, you die, that kind of thing. That's an easy way to kill people, like rather than like having a nuclear bomb going berserk. And obviously, like denial of service attacks is like very possible. Like unlike like our regular computers, like if you can like crash a computer, it's just like one computer which is being crashed. I mean, maybe if it is a server, then it's just one server that has crashed, and like probably those computers underneath those servers have been the ones that have been crashed. But think about it in a SCADA system, like if you can crash all these sensors by like just sending out a broadcast command to like these kind of things, they are gonna screw your entire critical infrastructure over there. So that is one scary thing. I mean, like even a small crash on these servers could affect the entire country or like the manufacturing plants, the SCADA system. And of course, all the protocol anomalies, who are the vendors who are not following the RFCs, you can use the fuzzer to basically like find out those things, and you can help the vendors patch those vulnerabilities and fix those things too. Here are some of the past articles, news articles that were out about the SCADA attacks. One of them was in Washington Post about like Al-Qaeda having a control over one of the power plants. But it was reported in Washington Post, there, right there. And there's the second one, which is Withek Boden from, I think, New Zealand or Australia, one of those two countries, where he got fired as a contractor, and he knew how exactly those control systems work. And he basically took over this control system and said, like, if you don't give me my job back or whatever, pay me a ransom, I'm going to introduce pollutants into your drinking water and like cause like a countrywide thing, which is like serious thing. And I think they gave him a job back or something, or like they took him down. I don't know what happened to that. And there was the slammer worm, which affected one of the nuclear power plants, and it was like the security defenses were down for a while. And there's this gas pipeline thing, and again, like this particular dude, he got hold of the gas power plants, and they took him down within 24 hours. So there are attacks which are going on, and it's, you know, like some people are aware of the security and like the need for security in these places, and they work on those securities. And I think everybody else should consider the same thing, the security in these things. And it's been around for a really long time. It's not like SCADA network has just come in like yesterday or today. I mean, like it's been there for like few decades now. So it's like high time like we consider security into these networks and keep going on. These are all the few protocols that you can see, which are like kind of like, what do you call, it's with a standard which people can use around. And there are like so many other protocols which are like very proprietary. So companies think that like if I have a proprietary protocol, like people won't know my protocol details, so they won't hack into my network, that kind of a belief. There are like few companies with that kind of a belief. But it's kind of like the time frame that it's required and like the interest for that particular hacker to know how much time it's going to take for him to hack into those kind of things. And out of these protocols, I'm just going to like discuss about Modbus, UNP3, and ICCP. And I'm working on OPC now and some of the IEC standards too. So probably in the future works for those. So stepping into the first protocol, Modbus, and it's like one of the most simplest protocol. It's very easy to implement, and the open source code for Modbus protocol is already out there. You can just, I mean, that's how most of the companies are developing. I think the Java code for like Modbus, I think it's called JMod, and you can just go download it, and like you can start your new company for like saying like I'm a SCADA software provider, and like start selling the product. All that you got to do is like create a fancy GUI for that particular protocol, and then like start selling your product. And it's pretty easy to get it. So, and it was developed in 1970s and late 1970s, and it's been sticking around. And initially it was developed for the RTUs and then like the ASCII portion of it, and now it's been like used widely on the internet too. If you see, this is the protocol detail. The first 2 bytes are the transaction ID. These vary on every single transaction with a unique client node. And the second 2 bytes are like the protocol identifier. They're always null. So if you see like the highlighted portion down there, like the first 2 I've just kept it as nulls, which is like the transaction ID. The second 2 nulls are basically the Modbus protocol identifier, which is always 0000. And the next 2 bytes is the length byte, which is like 6 bytes. Even though you have like 2 bytes for length, the maximum allowed length for a Modbus protocol is only 254. So if you see any length byte which is like greater than 254 bytes, there itself you can notice that there's an attack or somebody's trying to like fudge around with your data, that kind of thing. And almost, I'll show you like how many queries are there. Almost like all the queries, they have a length of only 06. So that's an easy way to like, if you're writing like an IDSC kind of a filter or something, that you can just mention it, like the length has to be just 06, not more than 06. And the next 1 byte is like the OA, which is like the unit identifier, which uniquely identifies every single node. Like I told you, there can be maximum of 200, where I said like maximum of 254 nodes. That's the maximum connection that each RTU can handle. And the next few bytes are basically all the, the 08 is like the diagnostic mode. I will explain that again like in the next slides. And the next 2 bytes are like the subfunction codes, and last 2 bytes are the data bytes. Here's the function code list. These are all the things that your server is going to do. Like if you send like 01, like it's going to ask the server to read the coil status and send you back the response for that particular thing. And if you see like at like the hex 11 value, which is like the report slave ID. So if you're like trying to do enumeration of your network, all you got to do is like report slave ID, report slave ID, report slave ID, and like get all their IDs and like their details about that particular nodes. That's like kind of like mapping of your enumerating your network right over there. There's some instructions which like the hex 09, hex 08, those are all like more of a proprietary kind of a thing, and even the hex 12 value. And there are like other stuffs which can be like really bad too. There's a like supposing you have an ongoing communication going on, like one particular easy way to like just stop the communication from happening is to like reset the communication every time, which is the hex value 13. Yeah. So you can just do those kind of simple things which are like very easy to do, but which can prove like a lot more damage for us in the longer run kind of thing. Yeah, if you've seen the previous slide, I didn't have 08, and because 08 is the diagnostic mode, and they take a subfunction code as well. And these are all the following subfunction code, and the interesting thing will be like the second one, which is like the restart communication option. So you can just keep on sending restart communication, and is there a reboot command here? No. That's in DNP3, yeah. So there's a reboot command there. And you don't want to be seeing any data, any instruction which is like above 16 over there. Clearly it's not like meant to happen there right now, at least at this point of time. Going on to the next protocol, which is DNP3, which is Distributed Network Protocol 3, and it's mainly and widely used in all the utility companies. And here's the architecture for it. Like the first 2 bytes is always the sync bytes, which is 0564, and the next byte is like the length byte. And again, here like the data packet cannot be more than, actually, like the length over here mentions the entire data, which can be like maximum of 250. But there's a funny thing happens in DNP3 protocol where like after every 16 byte of data, there's a 2 byte of CRC added to it. And they have a different kind of CRC. It's called DNP3, CRC DNP3, and I have that one implemented too if someone requires that. And it's kind of available outside too. And the next one is the link control, which ensures that like your communication is going on fine, and the destination address, source address, and the CRC and the data. Here are some of the internal indication flags that DNP3 follows, so which can be used against or in favor. These are like every single bit over there. Like it's a 2 byte thing, and like just taking 1 by 1 bit, like you can find out all the information about the server or the time that was stored and everything. And like I was explaining, in the transport layer byte, like this transport layer happens, in the data portion, like it's like the first byte in the data portion is always the transport layer byte, which says like if the first bit is set, it means it's like the first packet of the communication. If the second bit is set, it's the last packet. If both of them are set, then it's like the only packet of the communication, and goes on. And the next 6 bits are used for like the sequence number in the first byte. Then these are all the application layer, and like the DNP3, like I was telling you about, like 2 CRC bytes after every 16 bytes. Going on to the next protocol, which is like ICCP. And oh yeah, the other funny thing, interesting thing about DNP3 was like DNP3 was formed not exactly out of urgency or something, but like they wanted to have a protocol for all the utility companies, and while ICCP was being formulated. So it was like just like a quick thing that they wanted to like pull out from, like they took all the readily available things for like the IEC 60870 standards, and then they used it up for the DNP3 protocol over here. And that's how DNP3 was formed. And it was initially formed for the US, and then I think it just spread around. Going on to the next one is like ICCP. ICCP was mainly developed so that it can be like used in the WAN network. And they, how am I doing? So ICCP was developed mainly for like all the WAN networks, and if you see like they take into account like many of the security issues over here, wherein like you can have like all the initial, like they have like their own 7 layers after the entire TCP/IP communication is done, where like they have like their communication requests, and then there's like the transport this one, and I'll explain those things in the some coming slides. And there's like a bilateral communication table, which like every time you make a request to the particular server, it sees like, is this client authenticated enough to have these kind of data? Is it like a read, write, or like execute data privilege only, or he has no access to it? And based on those privileges, the access to the particular client is provided or denied. Then the application control service element, it's like used to like associate more connections. So like the ICCP one, since it's being like used at the higher level of the control systems, it's going to be like having more connections, and it's like built for using in the WAN. So here's the protocol summary of how ICCP looks like. The like different layers. Like the second one is like the connection, and like, I'll just go into it. This is TPKT. And like if you see in this protocol, it's just got 4 bytes over there. The first byte is the version byte. It's always 03. Second byte has to be null. The next 2 bytes has to be the length bytes. How could someone mess up this? Well, there's a big vulnerability on it which has been like disclosed on, and one company who implemented this was being used by so many other companies, and they're all vulnerable to it. But it's been patched and it's all secure. By now, I hope all the clients have also updated. So here's the simple structure, and then like following these 4 bytes is the COTP. The COTP is like the connection-oriented transport protocol, and the initial connections are like this. It's, by the way, like they are all connected together. I just didn't have a space, so like I had to break it up this way. So the first byte is like the total length of the COTP, then the PDU type, which says it's connection request or connection confirmed, and those are the 2 hex values that it has to take into there, and like the destination reference, source reference, and like the class options. Then next 3 things that you see, the value C1 in the first one makes it like it's like a source TSAP that it's requesting for, and like the parameter length, you say like 12, and then like you have like 12 bytes of data over there in the source TSAP. So that's how the length varies. And C2 and C0 is for the destination, and then the total size of the TPDU. Sorry, TPDU, yeah, that's right. Then this is like the data transfer portion of the COTP. Like initially, after like the TPKT is done, then like we have like the COTP connection request or and the connection confirmed. Once those 2 are done, then we have like the data transfer portion of it, which is like pretty lightweight again. Like it's just 3 bytes value, the length of the data that is going to follow, and then the TPDU value, the data transfer, which is going to be like hex byte 1, and has to take the value F0, and then like you have like the number of this one is, it just says if it's like the last data unit or like the initial one, that kind of thing. And then like if you see the highlighted portion again, it's like O2, which is like the length, and FO for the data transfer, and AT, which says like if it is like the first or the last packet. Sorry. Then this is like again like the next one, which is like the disconnect request at the end when you want to like terminate the request. Sorry. We have again like the length, the disconnect request, which is like 1 byte, which has to be value 80, and then like the destination reference, source reference, and the cost. So here's the other thing. Like if you are taking down an ICCP server, then you might want to like make sure like the cost is like put in like a something value, which is like not suspicious. The last byte in that one is like 81, which means like it's due to congestion over there in the other end that like the server is going down right now. Or is it like, if it is 80, then it's like normal cost, so like the server is going down because of normal cost. So these are all the things that people need to like look into it, so, and not expose these kind of details out. Now moving on into the fuzzer. So it's named Sully. It's named because of that guy from Monsters, Inc. And I've never seen. Well, it was Aaron's idea to name it Sully, and I thought it was a great thing because he's fuzzy. So, what is the SCADA protocol fuzzer detect? It detects all the protocol anomalies if they are not implemented to the RFC standards, those kind of things. Then if there's any unauthorized communication going on, like some of the byte values that you're not supposed to see, which goes in through the wire, those things are all determined by this. And then the possible denial of service attacks, which can be created by crashing the server, by sending in false status, those kind of things. And these are all the protocols that I'll be like discussing about. And again, I'm telling you, like, I'm not releasing the tool right now because of few requests. So this is the fuzzer's main components. There are so many other components. The initialize thing is just initializes the blocks. Sully is basically a block-based fuzzer, so it all takes in values which are in blocks. And like I told you, like since if you look at the PDU over here, like it all has like the length byte, which is just 1 byte, and then the PDU type, which is 1 byte, those kind of things. So like you just put in blocks over there and like add up your own fuzzers. And the primitives basically, the PET-RPC is used for the communication between like the VMware image and like your base host, that kind of thing. And then the primitives is the one like where like supposing if it is like an integer value, then like we mentioned it's like s_int and go on with those things, or like if it is a character or like a word, short word, all those kind of blocks are like already predefined over there, so like with all the fuzzing test cases built into it. Then sex.py is the Sully's exceptional handler. And the different agents over here, the agents are like one of the neatest thing about this particular fuzzer, and I'm sure like Pedram and Aaron, they worked their asses out on building this. And it was like network monitor, which makes sure like all the connections is fine, and then like logs up all the PCAPs and everything. So like if one particular thing crashed the server, you don't have to like redo the entire thing to do it. So you can just collect the PCAP and see what particular value was it, and like you can keep on running this one. Then there's a process monitor, which sees like if the process got killed or like the CPU usage of the process, shoot it up, those kind of things. And the most elegant thing about the Sully fuzzer is like the VM control. So if you're running on a VMware image, your entire the test case, like the software application over there, and like you're like sending out all your test cases from your base host, and like at one particular time it crashes. So there are cases like there were some softwares that we tested, not the SCADA softwares, like the other softwares that we tested. When it crashed, even like a reboot of the image didn't give us back this one, what do you call it, good working condition of that one. So we had to go all the way back to like the known good state. And with VMware image, it's like really amazing how they can do it, and then like it just like reverts back to the last known good state, and then like keeps running the test cases again. Here's the general architecture of the Sully framework, how it works. Like there's a data generation portion, like the big gray box over there, and then the session controls, and it does all the blocks basically and the graphing of it. And the other good thing about it is like it looks since it's all graph based, so we can like see like at which point like the decision was made into go into different places, and like sees what other options can be given to it, so like what other options can be given to go into like different code paths. And it covers like it's more of like it covers like the entire code base of the software, so which makes it much more useful and finding out like if there are any bugs in like different portions of the software, rather than a traditional one where like you just say like, okay, this is the software implemented for Modbus, so like we just check for like only these controls, whereas not bother about like the other operations, like which might be like an added advantage of the things. So the first one is like the web GUI of the the Sully fuzzer, how it looks, and the side one is like the book that Pedram has written on this, not just Sully, but like all the fuzzing and everything, if you want more information on Sully. Here's the code snippets of like all the protocols that I've just discussed. Like the first one is basically like the initialize, and all the things have to have an initialize. Then like, there's the static portion, which is like over here, like the transaction ID. Sorry, I'm just keeping it static because I don't care if like the transaction ID goes about. Like if you want to like change it, you can like use it like a string or like char and like short word, and then like fuzz that transaction ID as well. And then like there's like the length byte, and then the protocol identifier, and then the length byte. Again, like the length is also like, since it's a block-based fuzzer, so if you're adding more data in like the in-between portion, like the sizer will automatically increase the size and like fuzz it on that basis too. So this is just an easy reference with the protocol over there. And the DNP3 code snippet is somewhat like this, where you have like the first 2 bytes, which is like the sync bytes, then like the static length. This one I've done it with the static length, so I haven't included any of the values over there in the below. Then the DNP3 uses a special CRC, like I told you, so you have to follow that particular thing. And this is TPKT, which is again like just simple thing, which is like just 4 bytes value, and you can fuzz in like every single thing. And CRTPE and more. Okay, I can show you the demo. This software I just like downloaded like the demo version of this software and like the first software that I found, and then installed it, and like I'm just ran the fuzzer. Yeah. Sorry? I can't disclose that, sorry. And I'm like holding on. I'm like really like working on this one, the response. No, Sully is released. Yeah, Sully is released. Just the SCADA portion of the Sully fuzzer, like all the test cases and everything, those are not being released because I mean like Sully has been like mainly developed by Pedram, so it's his tool, and like he is releasing it. And the fuzzer portion of it is not being released. If you don't have to reverse engineer it, you can build your own if you can read the architect. I mean, like how the protocol works. So, whatever the work I did cannot be released because I don't want to fall into any of this. So I've attached the debugger to it, and I hope it works. Oh, great. I know. I think the internet is not there. Connection. Yeah, I've turned off my wireless, so I was hoping my VM network was connected, and it is. There you go. Oh, yeah, I know why, sorry. I'll open up the port here. So I opened up the port for this particular. This port is open. I can just show you that. So if you see the port fire tool, which is like the Modbus port, which is open right now. Yeah. So these are all the fuzzing test cases that are going over there, right there. If you saw in the background, it just crashed, and I'm not disclosing anything else about that. Sorry, I had to. And like, these are all the different like as I explained before. Like if you see it clearly, like the first 2 bytes with the transaction ID, the second 2 bytes of the protocol identifier, which is not the next 2 bytes of the length, which has to do with the particular length of the protocol, and then there's the OD is the unit identifier. Then the next one is like the diagnostic mode, the 08, and the following is like the subfunction code, which is like the reserved or unreserved portion, and then like the other data portion, which is all there. So there's a huge bunch of things. So we don't know which one crashed it. So sorry. So that was it. And if you do find bugs in, let me just finish with my slides, sir. So I would recommend being responsible in your disclosures. Please don't go and hack into anybody's SCADA systems, and please don't cause them a lot of trouble. And we being, as part of Tipping Point, we do buy vulnerabilities, and you get paid for it too. And we do a lot of responsible disclosures where like we talk to the clients and like we make sure you are, I mean like the vendor is not being exploited in the meantime. And then like since our IPS can does, like we can write the signatures for it for like at least our own clients too. Sorry? I have no clue, sir. I have no clue, sir. Conclusions is like, and everybody wants to make money, right? I was releasing it for free, and like now even I'm not doing that. Okay. You can try talking to the ZDI program and see what it's like. And the conclusion is basically the basic SCADA network architecture that I discussed to you guys, and like, the why we need securities over there, and like SCADA protocol details that I gave you, and the fuzzer details. So if you want to build up not just for SCADA, for any other reasons, you can do it. And the black hat slides for like the Sully fuzzer is also out there, so you can use that one as a better guide too. Future work will be like to have like more SCADA protocols and like two-way fuzzings. Supposing like in the case of ICCP where you send connection requests and then like send in all the fuzz data and then like pretend to be like the guy who sent back the connection response, and then like yes. And we do have ASN1 decoder in Sully too. Let me just, and these are all the references that I have. And those architecture slides, I got it from someone. I don't know who, so that's why I don't know. And acknowledgements for these guys. Yes, sir. I am not from that community, so it's like mostly like the lateral thing. And like I know like there are so many companies who just go out and like build softwares and like just release it right there. I'm like they just want to get into the market as soon as possible rather than like wait for like all the entire testing of their own product. So. Yes, sir. Well, what if there are cases where, like, say, there are people who do patch their systems, right? There are people who patch their systems regularly.
The vendors have to supply the package.
Patch too.
You cannot just go out and arbitrarily patch a SCADA system.
We can do it. The vendors have to do it. So if you do find some...
Has a hammer, so they're getting nails. The problem is the wood is rotten. Yeah. And they don't have wood rot tools. So give them some credit for banging on the nails. Yeah. But remember, the risk isn't there. The risk is somewhere else.
Yeah.
So is GE held accountable for the power outage for their SCADA devices?
Why would they take responsibility? They will say like the vendor was not safe or something. I'm like the place where it was implemented, they didn't do a proper job. It's always going to be like one person kicking the other person's back, that kind of a thing. So just let me finish up. Good.
What's even more scary is most of your medical control systems, like your MRIs, your CAT scan equipment and all, you know, run ancient versions of an OS for whatever year the equipment was manufactured. And in that process, you have to get FDA approval before the vendor can turn out patched software. So you get medical instrumentation that is infected by viruses and worms, where they literally have to yank out the entire CPU and put another CPU in and hope that it doesn't get infected.
Yes. I'm like, that's how it is. I'm like, there are people, but the good thing is like, at least now the SCADA vendors, there are many people who go about patch this one. Like, more than us, I think US CERT has been like hitting the hammer. I think they got like a steel hammer a little bit. No? I don't know. At least like, they seem to have more advisories out there. I'm like, I'm sure like all the smaller SCADA vendors, they don't even give a damn because they say like, we don't have such a big customer base. Like we're just going to like sell our products to like these small manufacturing units, those kind of things. It's like those small manufacturing units in the later years when they become big and they're still using these softwares, that's when they're like much more exposed. I mean, when you're small, nobody cares. Once you start growing, that's when people start noticing you and start trying to attack you.
Every major EMS on the market uses RCP and RSA.
So that's true, but like most of the cases is like they want to say like, oh, we support this protocol, we support this protocol. So like their data sheet becomes bigger and like they can like sell their product. That's how they try to do money. And like.
Every major EMS runs RSA and
There's some people.
critical communication in 2007. Every one. Only three. This is the large.
Sir. So the fuzzing will be much more useful like in the case like where like the vendor wants to test his protocol before releasing it out to the, you know, like. I don't think they're going to raise their hand over here and say like, I'm a vendor over here of SCADA. To respond to the other one, some of the SCADA networks don't even have a firewall in it. So yeah.
Siemens has a Bluetooth controller for PLC.
There's a guy who's interested in that right now. Yes, sir.
There are vendors here, it may not be Black Hat or Defcon. There are some security data conferences. There are a set of vendors who have some awareness who care about these things.
Yes.
It's not the
Yeah.
mission marathon. There's some groups doing some work here. It's not great. Many years behind the internet maybe, but all hope is not.
Yeah, I know. Like, I really appreciate like some of the vendors. They like once like they've been notified about the vulnerability, they go about patching it and sending out new updates right there. And ICCP was one of them. Takebishi is another one. Like they all do this kind of work. And like it's like the people are taking interest. Like it's just like the rest. I'm like there are like so many small vendors who don't give a damn about it. I'm like, and those small vendors are like the cheaper ones, which are being used in like all the smaller networks. Maybe like all the major critical infrastructures, they pay big money for like the big vendors, and just because they have this brand name over there, they use that kind of thing. But even they are vulnerable. But like. Yes, sir. One's there.
To what extent, I know this isn't classically thought of as a SCADA system, but to what extent did you consider, did you look at, were able to test the emergency broadcast system, the digital part of that? And the last that I heard anything much about that, there wasn't authentication. So if you have a low power radio broadcast that you can bring up to the next side of a big one, boom, instant cascade.
So,
Yes, please don't. That's why I'm interested in compensating control. That's why.
But
I'm interested to know if this was considered.
but there are like protocols which have been implemented which are allowed to travel through wireless too. So, just
Did you look at those, consider those
No.
as part of what you're doing?
I haven't. I'm just looking at the protocol stack right now, and I haven't had a chance to like go inside like the real thing and like do it. And like I don't intend to do it either. Like into like a real control system and like screw up somebody's network. I don't want to do that. I don't want to be part of it. Yes, sir.
For you applying, you wrote the logic or you the script in the scope.
So the Solid was like the base framework. So the framework is built, and like I used my scripts for all the SCADA protocols.
You use Scala to run it.
Yep.
Are you implementing, is Tipping Point implementing any of these SCADA signatures in any of their products?
Yes, we are.
When?
They're already out.
They're released.
Yeah.
So DMP over IP, Modbus over IP, ICP are currently available for your
Yeah.
products.
Do you want to buy us? Yes, sir.
What do you recommend doing about, all the legacy systems out there that have been installed for 20, 25, 30 years, introduced by vendors that no longer even exist?
Buy new ones.
Talking about,
It's going to be freaking expensive, but like
they're spending tens of millions of dollars, to replace,
they haven't spent for 20, 30 years, then I think they can spend now. I'm sure they made enough money to be surviving for 20, 30 years. Buy an IPS, yeah, rather worse. Well, I'll be in the Q&A room if you guys have more. Thanks.